Graves from IDA CCS, otherwise known as the Center for Computing Sciences. And the title of her talk today is "The ABC Conjecture Implies That Only Finitely Many Cullen Numbers Are Rep Units."
So, hi everyone, my name's Hester. I work at the Center for Computing Sciences. And after I give a talk, I wish people asked about my math, but they normally ask, what's the Center for Computing Sciences? Why aren't you at a place with college or university in its name? So we're at a think tank, and there are lots of great reasons to work at a think tank, as in there is a large number of mathematicians to work with and play doing mathematics. My research has been with John Grantham, who I work with, and the two of us are hosting a breakout room in the afternoon if anyone wants to know what it's like to work at a place other than a university. So today I'm going to be talking about some work we did showing that the ABC conjecture implies that only finitely many Cullen numbers are rep units. I realize this is a pretty technical title. There are lots of words and phrases in there you might not know. There's the ABC conjecture, there are Cullen numbers, and there are rep units. And this can be extra confusing because, as John found out when he found us some rep unit swag, there's more than one meaning for rep unit. Apparently, it is also a weightlifting term. That is not the sense in which we are going to be using the phrase rep unit today. So I'm going to start by explaining what all these technical terms are. So the first thing we're going to talk about are the Cullen numbers. The sequence C sub n, which is equal to n times 2 to the n plus 1, where n ranges over the positive integers, are the Cullen numbers. And since we're mathematicians and more specifically number theorists, one of our most natural questions to ask ourselves is, why 2? Can you put something else in there, right? I think that's half the talks in math, why 2, or in number theory, or why p. So this leads to the more general definition. Come on, computer. The S Cullen numbers, where we replace 2 by S. So these are numbers of the form n times s to the n plus 1, where s and n are positive integers, and s is greater than or equal than 2, because s equals 1 would be silly. It would just give you n plus 1, and we know everything there is to know pretty much about n plus 1 when n is an integer, right? You can figure out what the next guy in that sequence is. So the next question you might ask is, why do we care? And different mathematicians are going to have different answers. I self-identify as a elementary number theorist, which means that when I see something that looks like n times 2 to the n plus 1, my immediate reaction is, oh, that's cool. But not everyone self-identifies as an elementary number theorist. Some people like theory, some people like challenges, some people like status. For the third group, I'm going to tell you, you should care about Cullen numbers because Hooley cared about Cullen numbers. Hooley showed that almost all Cullen numbers are composite. It is conjectured that there are infinitely many prime Cullen numbers. There's been further research on them. Luca, and I know I'm going to mispronounce this name, I'm sorry for the rest of the talk. Math is an international endeavor, but we don't speak every language on the planet, and I will mess up names. If someone knows how to correct me, please interrupt and correct me, because I don't want to be rude to any of our colleagues. Luca and Stanica showed that there are only finitely many Cullen numbers that are also Fibonacci numbers. And Marcus then generalized this result to S Cullen numbers for fixed S. And then Bilou, Marcus, and Tobey then expanded this to other recurrent sequences. All right, I think we now know what an S Cullen number is. And spoiler about this talk, the title of the talk really should have been "The ABC Conjecture Implies That There Are at Most Finitely Many S Cullen Numbers that are rep units for a fixed S." But that is too long. So that's why I just said straight up Cullen numbers. Okay, so the title, we said the ABC conjecture implies there are at most finitely many Cullen numbers, really S Cullen numbers, for fixed base S, that are rep units. And we now need to talk about what are rep units when we're not talking about weightlifting. So a rep unit is a positive integer n that can be written as 1, which is a unit, repeatedly. 1, 1, 1, 1, 1, 1, 1, 1 for some base b. And so what does it mean when you can write it as 1, 1, 1, 1, 1, 1, 1 for some base b? That's the same thing as you can write it as b to the q minus 1 plus b to the q minus 2 plus 2, 2, 2, 2, 2, 2, 2 plus b plus 1. And you can see we can write that in summation notation. And that is the same thing as b to the q minus 1 divided by b minus 1. And you should be thinking, oh, cyclotomic polynomials, we love those. These are natural. I'm paying attention. So this is, we restrict ourselves to some integer base, which is bigger than 1. Again, because if b equals 1, we end up with something silly. And with some integer exponent q greater than or equal to 3. Why not q equals 2? Because any number n, where n is bigger than or equal to 2, can be written as n minus 1 plus 1, where n minus 1 is non-zero. So that means any n is 1, 1 base n minus 1. We're not messing with that, right? We just said we're not dealing with the sequence n plus 1. We know too much about that. So what are some examples? 1, 1, 1, 1, 1, 1 is a base 10 rep unit, and 7, which is equal to 4 plus 2 plus 1, is 1, 1, 1 base 2, and that's a rep unit base 2. All right, so we have talked about Cullen numbers. We have talked about rep units. Now we need to talk about the ABC conjecture. And to state the ABC conjecture, we need to know what the radical of a number is. So if n is a positive integer, we can write it as a product of prime powers, p sub I to the a sub I. And the radical of n is just the product of the p sub i's with the powers greater than 1 stripped away. So the classic example, 90 is 2 times 3 squared times 5. Its radical is 2 times 3 times 5, or 30. So the ABC conjecture of Oesterle and Masser is if a, b, and c are relatively prime integers such that a plus b equals c, then for any epsilon greater than 0, there are only finitely many exceptions to the equation. C is less than the radical of a times b times c raised to the 1 plus epsilon. This is actually a very simple statement, but it's intimidating to people who don't like epsilons, which is a large percentage of mathematicians who do not self-identify as analysts. Fortunately, for those people, in this talk, we restrict ourselves to the scenario epsilon equals 1, so you don't have to look at epsilons again for the rest of this talk. So let's look at our subset of the conjecture. If a, b, and c are relatively prime integers, such that a plus b equals c, then there are only finitely many exceptions to the equation c is less than the radical of a times b times c squared. Probably should have said that as the square of the radical, because I can't point at things because we're on Zoom because this is COVID. All righty. So the theorem we're actually going to be proving is that the ABC conjecture with epsilon equals 1 implies that for any fixed integer s greater than or equal to 2, there are only finitely many s Cullen numbers, c, sn, that are rep units. Now, I was always told, don't prove things in a talk. It's boring and you're going to lose people. But again, pandemic, all rules out the window. So I'm actually going to prove this for you. Also, the proof is really easy and short, which helps. So there are two parts of this proof. Rep units have length 3 or greater. And we're going to prove this for rep units of length 3. We're going to show that there are finitely many. Then we're going to show there are finitely many for length greater than 3. And when you take the union of two finite sets, it's still finite. And therefore, we prove our theorem. I'm going to do the first part actually with all the details. And the second part, I'm going to do a little hand waving, but there's no content in this hand waving. So let's look at S Cullen numbers that are rep units of length 3. If we have a Cullen S number, a S Cullen number, it can be written as n times s to the n plus 1. And if it can be written as a rep unit of length 3, there exists some b, so that it's equal to b squared plus b plus 1. And I don't know about you. I look at this equation. I say there's a plus 1 on each side. You got to cancel it. So ns to the n is equal to b times b plus 1. And when you see that b plus 1, it is screaming use the ABC conjecture, because b plus 1 is equal to b plus 1. b1 and b plus 1 are all relatively prime. So for all but finitely many b, we have b plus 1 is less than the radical of b times b plus 1 squared. Well, we just said b times b plus 1 is the same thing as n times s to the n, and that radical is certainly less than Sn, and we square that. So now we have b plus 1 is less than s squared n squared. Well, let's go back to our equation up above. N times s to the n is equal to b times b plus 1. That's less than b plus 1 squared. Oh, wait, we can substitute in for b plus 1, and we can see that n s to the n is less than n to the fourth s to the fourth. And you got to divide through by n and by s to the fourth. And then you can proceed to take log base s. And that holds for all but finitely many values of n. So we've just shown this for all but finitely many values of n, all but finitely many values of b. Boom. There are finitely many s-Cullen numbers for fixed base s that are rep units of length 3. So now let's look at the case, I told you it was short, for when you have length greater than 3. So let's do the same thing. We take our generic s-Cullen number and we write it as a rep unit of length, a rep unit base b of length q, where q is greater than or equal to 4. And we still have this plus 1 on both sides of our equation, so we get rid of that. And we can see that we can factor out the b again. Same thing as in the last proof. But we're going to multiply both sides by b minus 1. And we're going to see that the right-hand side has this b to the q minus 1 minus 1. And we should now be thinking, whenever we see a plus or minus 1, this is a great time to use the ABC conjecture. So if you can apply, if this is one of the b's for which the ABC conjecture works, we would have b to the q minus 1 is less than the radical of b to the q times b to the q minus 1 times 1. And that's going to simplify to the radical of b times b to the q minus 1 minus 1. And we're only looking at the case where epsilon equals 1. So here we go. So this is assuming that this is one of our, that we can use this, which is true for all but finitely many b. Then we can take this b to the q minus 1 and replace that with b minus 1 times n s to the n. That was the last equation on the last slide. And we square it, and we expand. And this is still true if you subtract the left-hand side by minus 1, or if you subtract minus 1 on the left-hand side, divide both sides by b minus 1. You can then go through and, oh, what is this? Yes, you divide both sides by b. No, you multiply both sides by b. Turns out you can multiply the side on the right by b squared. You get an inequality. You do the same thing where you divide by powers of n and s to clear things out. And you can just do a little more fun with bounds, take logs, and you get your result. So keep in mind that our theorem was we fixed s and we let n vary, right? We looked at all s-Cullen numbers for a fixed base s. So you guys might be wondering what happens if we fix n and let s vary. Well, the most basic example would be n equal to 2. And so you might say, what's going on with if you look at the collection of s-Cullen numbers where n equals 2, right? That's 2 times s squared plus 1. And as happens whenever you do anything fun in math, of course Euler already did it. Let's check this out. Let's look at the ones that are rep units of length 3. We've got 2 times s squared plus 1 is equal to b squared plus b plus 1. Or if you do a little rearranging, you've got s squared is equal to b times b plus 1 divided by 2. S squared is a square. B times b plus 1 divided by 2 is a triangle. So these are the square triangular numbers. and they were characterized by Euler, which gives us an infinite family where if we fixed n and let s vary. So we've got to have the conditions we have in our theorem. Now, we show that there are all but finitely many exceptions to our theorem, but it makes sense to look at what's going on computationally. We have no idea how many of these exceptions there are. So we did these computations, and there are no S Cullen numbers, which are also rep units, with S less than or equal to 75 and n less than or equal to 75. That was one computation. Or S less than or equal to 10 to the sixth and n less than or equal to 10. So the pre-code for this is available on GitHub. And if you want to check this out in detail, because of course, not only did I make mistakes because it's a talk, it was all done very quickly. So if you want to check out the details, our paper is on the archive.
All right, let's thank Hester for her talk. Are there any questions?
Okay, I do have a question. Sorry, you just have to wait long enough for someone to say something. So you said you've for a fixed s, there are finitely many, but now as you increase n, like this, Euler has this example where like you have an infinite family.
That's if you fix n and let s vary.
Or did I say it backwards? Of course I said backwards. How quickly do these grow? Does that make sense?
How quickly do they grow? Don't know.
Okay.
Well, those are easy to characterize. Like Euler's thing is like a Pell equation. Like you can write down what the Pell equation is, and that's units in the quadratic field, basically. That's what I'm saying. Like, so you can easily solve that.
Christopher, yeah.
Sorry, I'm not sure how this works. First online conference. So how effective are these finiteness bounds? So if I fixed an S, can you tell me like there's at most this many n's for which these are a rep unit, and how do those compare with, I don't know if you've done some of these computations, how do those compare with the actual number of Cullen numbers which are rep units?
So sorry, you're asking about how effective is the ABC conjecture?
No, sorry. So you're using the ABC conjecture to give finiteness, but I guess I'm asking, is there anything effective that you can say?
Not that I know. John, is there anything? Yeah.
So I can't remember who it was who suggested it to us, but we would have to work with an effective version of the ABC conjecture.
That's right. Waldschmidt suggested this.
And
right?
we haven't done that.
Yeah. Waldschmidt suggested this, and it sounded like the sort of thing that I don't have the time for right now. This would be great for a grad student who is interested in these sorts of things.
There we go.
Yeah.
Waldschmidt basically was like, why don't you guys go ahead and do this? And I was thinking to myself, I don't have time to do this. But for someone who's looking for something to do, this would be a great thing to do.
Yes, I have enough papers that I've done the research for, but not written up, and I don't want to add to that.
We have three together we're working on, and it's just, who knows when one of them is going to get finished.
So the other thing I will say is that I believe, we did these computations, I don't know, 6 months ago, but I believe it's the case that the square triangular numbers were the only exceptions that showed up. So I guess it might be interesting to see how close to that you'd get, but I mean that's essentially one at most for each S. So But yeah, with an effective version, it would be interesting to see how many are the bound gives. I mean, it's a conjecture. You can always assume stricter and stricter versions of it and see what happened to that. So,
are there other questions? Okay, if not, let's thank our speaker again. Okay, I believe we have a lunch break now, and then our next plenary talk is at 1 o'clock in the other Zoom room in room 1. So we will see you there.